I can't believe how quickly this week has gone by. We are already here for the fourth talk in this series, in this lecture series. And for our audience, for our local audience, of course, our speaker now needs no introduction. You know what to expect. Thibault is a remarkably versatile young physicist. His work spans the range from having created some of these codes for doing calculations, ranges from there to analyzing models to understand experiments. But just for the audience that might watch this recording in the future, let me remind you that this is the fourth lecture of the 2020 Michelson Postdoctoral Prize lectures. The Michelson Postdoctoral Prize is given annually by the physics department at Case Western to an outstanding early career physicist in any subfield of physics. Our prize winner this year, the 24th recipient of this award, is Thibault Sohier, and he's going to tell us about something completely different today, materials design and discovery. So welcome, Thibault, and the floor is yours.
Thank you. Well, let me start by thanking you for this wonderful week. I mean, since the last lecture, I should really reflect on this week, and it was really great. A lot of very nice discussions and nice lunches and dinners and the talks. I enjoy giving them as well, and hopefully you'll enjoy this one as well. So this one is a bit different. There's a little less physics in there, a little bit more of a materials design, but it is motivated by all the physics we've talked about. And we've talked about some of those things on Monday already, but very briefly, we'll go a little bit into more details here. So again, I acknowledge the people that helped me getting there. This work, materials design, I really started seriously during my postdoc at MPPL, so with Nicola Marzari, that is very much into this idea of finding new materials. And I'm continuing it to this day. Okay, so this is the outline. We're going to talk about this high mobility quest that I've been going on for a few years now. Then we're going to look at the tools I use to go on this quest. So density functional perturbation theory in 2D, we've already talked about it yesterday. I'll just go very briefly over it. I'll talk a little bit more about the transport workflow this time. This is used to compute the mobility and conductivity in materials. And then we'll go through 3 applications of all this to materials discovery and design. So some valley engineering in arsenine, profiling high conductivity materials in general in the database, and then remote screening. That's kind of a neat little application of Van der Waals aerostructures. Okay, so to start, you already seen this slide, but it's good to remind. This is the starting point of all our design and discovery of materials in 2D, at least. We start from a database of 2D exfoliable materials. This was obtained by first collecting all experimentally known bulk materials. And then from there, we identified the layered structure using some geometric algorithm. And this algorithm is pretty good at finding some non-obvious layers, like those that are interlocked like this one, or some that are in some non-obvious directions, like this one here. Oops. So once we have identified those layered structure, we compute their binding energy. So we compute the energy of the bulk material and the energy of the isolated material. The difference is essentially what you need to the energy you need to it costs to exfoliate the material. And then we plot the binding energy as a function of a parameter that tells you how much Van der Waals interactions there are in between the layers. And so materials with low binding energy and Van der Waals kind of binding are those that will be easily exfoliable. And in this blue cluster here, we find all the usual 2D materials that are already known experimentally today, plus 1,000 others. So that's a good starting point to start and explore and find new 2D materials that would be interesting for this or that application.
So this might be a little bit tangential, but how do you determine those distances? Is it just measured, or
the distances?
The x-axis, the interlayer distance.
So this would be a delta of interlayer distance between in the DFT calculation using two using two different kind of functionals, with or without van der Waals interactions. And so admittedly, supposedly, the distance changes a lot whether you or not you include van der Waals interactions in materials that are bounded by van der Waals interactions. That's the idea behind this parameter, but yeah, it's not very intuitive.
I have another question. In studying these geometric aspects of finding these layered structures and then calculating their binding energies, do you see any effects of when, that they are more bonded if they are interlocking, or do you see any geometrical effects that might make it more difficult to exfoliate them if they are interlocked like that?
So I think experimentally it might be more difficult to exfoliate the interlocked one and things like this. To shear them, yes. No, we don't see this. We do the calculations with and without, so it's not exactly how it's done in experiment, of course. And so it's just an indication. Then, well, hopefully, if experimentalists are interested in one of those, they can try and tell us if it's more difficult when they're like this. This would be interesting. But yeah, no, we don't know. So from this database, then there are various projects, different people in the group. We're looking at, at topological materials, superconductivity, catalysis, various applications. Mine was about conductivity. So in this database of around 1,000 easily exfoliable materials, first of all, I focus on a subset of those to start with. And there are around 250 that have small unit cells, so with less than 6 atoms per unit cell. And I took those and I asked myself how to find high conductivity semiconductors among this subset. And so to kind of frame the quest, here is what we're looking at. We're looking at phonon-limited charge transport in gated 2D semiconductors. Phonon-limited means only electron-phonon scattering, no electron-electron, no impurity. So it's an ideal material at room temperature where phonon should dominate. We're looking at semiconductors, so materials with a gap to kind of turn off and on this current and this conductivity. And we are doping the material, so putting electrons in the conduction band or holes in the valence band with electrostatic doping, so this field effect transistor setup that I've been talking about quite a bit. The objective is to find high conductivity or mobility. We're doing this because there's a bunch of applications that would benefit from high and efficient, fast and efficient electron transport, but also for just the physics of electron phonons scattering and trying to understand trends at the level of an entire database, so hundreds, thousands of materials rather than just one specific material. And so how we're doing all this, so either we're looking at materials that are intrinsically good, that's more discovery, or we're trying to engineer their properties, and that's more the design part. Okay, this I've talked about at length yesterday. This is the first tool to compute phonons, electron-phonon interactions in those 2D materials. I've mentioned that the standard density functional theory is not adapted for those systems, so you need to apply a few modifications to deal with periodic boundary conditions properly, and also to implement the electrostatics of the field effect setup. But this is something that we have and that works quite well. So as I said, today I'd like to talk a bit more about the transport workflow. And there are a few other methods to compute transport properties from ab initio out there in the literature. I developed my own with automation and accuracy in mind, and I'll go over through the points that differ a little bit from the other methods, the things I do a little differently. So first of all, I use this tool that's called AIDA, and that allows us to write some workflows that are like big scripts that tell this code what to do, a sequence of calculation, ab initio calculations, to go from a simple property like band structure and phonons to a complex one like the conductivity or the mobility. Essentially what AIDA does in the transport workflow case is that it starts by analyzing the band structure and the phonon dispersion that we already have this information on the materials cloud. This is this database of 2D materials for which we have actually computed a bunch of properties including the phonons. So we start from there, look at what information we have there, and we try to select the electrons and phonons that participate to transport. So not everything is relevant for transport. In particular, only the electrons around the Fermi surface are going to participate to transport. So you can limit to those, and then you can look at which phonons are interesting to scatter those electrons around the Fermi surface. So we select those states, then we compute the corresponding electron-phonon couplings using the code I just mentioned quickly before. And finally, we plug all this in the Boltzmann transport equation that is then solved numerically. And all this is automatized with AIDA. Okay, so I'll go in a little more details on this, what this AIDA thing is. So it's essentially a interface between the users and the high-performance computing clusters. And there are 3 parts. So there's an API, so the user interface per se. And this one is a Python code that you can like write scripts in, and you can also use it in a Jupyter notebook. That's usually what I do, and it's very, I think, user-friendly once you master basic Python and Jupyter. The other like super important part is what they call the daemon. So this is some little processes that deal with the communication with the clusters. So it takes care of taking your calculation, preparing the input, like the text file of the input of the calculation, copying it on the cluster, launching the calculation, checking periodically whether it's finished or not. When it's finished, it retrieves the result, analyzes it, and potentially sends some other calculations. And yes, and all those SSH communications are dealt with by the daemon. I don't actually do anything there. And the third very important part is the storage, and it's a database in which every input, output, creation time, computational time, every information you might want to have about any calculation is neatly stored in this. So in effect, like for the past 6 years, I could go back on any calculation I've made. I have everything I need to redo it exactly as I did at the time. So this is great for reproducibility, which is very important for open science and the fair data principles. And it's also great for sharing. I can share parts of my database with other people, as usual. So this is a bit of like computational science details, but it's very like an essential tool that I use every day, so it deserved a little slide. Okay, a little bit more physics now. So as I said, for the electron-phonon scattering, we're not interested in every electron or phonon state. And this is inherently included in the way I sampled the states in this workflow. So we sample only the relevant states, so those around the Fermi level. That gives usually, here in the case of the conduction band of a semiconductor, that would give a little pocket of electrons at the bottom of the conduction band. Here, if we have a single valley, but this is what we see here. And then in every electron-phonon scattering processes, you have 3 kind of entities: an initial state, electronic state, a final electronic state, and a phonon that brings one to the other. And we need to sample all these things. The initial state, thankfully, can be reduced to the irreducible wedge of the Brillouin zone. So there are a few, a little bit less. The final states can't, because you also have the symmetry of the phonon there that breaks all the symmetry of the crystal, and so you have to take into account all final states. And then the phonons are all the momenta that link any initial state to any final state. And we take those, reduce them by symmetry, and this is what then we're going to compute. So the cost of the calculation is proportional to the number of phonons you're going to use. This is really the bottleneck, computationally speaking. And the interesting thing here is that all those grids can be chosen to be more or less coarse independently. Then the workflow takes care of mapping or interpolating on from one to the other. And this can be very useful to optimize the computational cost.
So there's an adaptive algorithm to choose the grid?
So to choose them, no, it's kind of a manual thing with some help, like hard-coded defaults that help you go towards like something nice. But there's still a kind of a human-based approach here. Usually, I'm used to it, so usually it takes me like a couple minutes to find a good one. But yeah, there's a little bit of a human thing. It's not fully automatized. Yes.
So to be clear, this is still a step you do by hand individually on each case.
Yes.
It's not like you set up some criteria and the computer decides on its own.
No, but we're very close in the sense that it probably takes me like 10 minutes total, like to launch the full of one material, which is really negligible when you consider like the time you could spend on some other methods. So yes. And so the last part I want to talk about is the Boltzmann Silver. Here there's no like big conceptual breakthrough in how I do things. It's just like a few little modifications that make it like relatively robust and work well also with automation. Because when you want to study like dozens and dozens of materials in parallel, you want to have something that's very robust, that will work for any material. So we've already talked about the Boltzmann transport equation. The game is to find this perturbed distribution of the electrons. That's this perturbation in the distribution is driven by the electric field that generates the current. And you have also some scattering that kind of randomizes the momenta. And you have to take into account this. So there's an ansatz for this perturbation. Yes?
Question on this. So in terms of linear response, F1 distribution, right?
Yeah.
So what about the anomalous velocity, the V cross omega, the very curvature? If there are some material that like you have anomalous velocity omega cross E, and then
no, this is not in there. So this is the linear, the contribution linear to the electric field, first order kind of thing. But yeah, interesting to look at those. The model will, the solution would probably have to be found a bit differently. But yeah, that's nice stuff to look at. So yeah, in this case, just this simple ansatz that's proportional to the electric field. The velocity that we know already is just, as soon as we know the band structure, we know the velocity. There's a temperature term coming from the derivative of the Fermi-Dirac distribution. And this is the unknown, essentially, is the scattering time that is due to electron-phonon scattering. So this is what we need to find by solving this equation. The equations, that is actually a system of equation with the size, that is the number of electronic states that you consider in your sampling. And each of those looks like this, with the scattering time for one particular electronic state depending on the scattering times of all others. numbers, so they're all coupled. And you might remember for graphene, I solved this by inverting a matrix, so more like an algebra kind of a solution. This was because with graphene I had all the analytical electron-phonon coupling matrix elements, and I could do a bit further analytically in this equation. Here, this is supposed to be solvable for any 2D material, like without knowing what's happening before, and so we need a much more general and robust solution. It turns out that the iterative solution works pretty well. So we start from a guess about the scattering time, put it into the equation that gives us a new scattering time, and we iterate until the differences in 2 consecutive scattering times is not too big. And here there's also a couple of tricks about using symmetries. I go back and forth between the Brillouin zone and the irreducible Brillouin zone to gain a little bit of time on computations. Finally, the very important trick, or numerical trick, is how we deal with those delta functions that are in the Fermi golden rules. So usually numerically you have to use some kind of Gaussian smearing to deal with those deltas, because you can't put the deltas numerically. And the problem with Gaussian smearing is that then you need to do a convergence test on the smearing parameter. And this is not very compatible with automation. This can take quite a bit of time. And so instead here we use exact integration technique with triangles. So this is the triangles method is the equivalent of the tetrahedra method in 3D, but here we're in 2D, so it's just triangles. And essentially what it means is we tessellate this surface that we see here, like the band structure, tessellate it, and then every function is interpolated at any given point linearly in those tessellation of the surface. And there's no need for convergence tests with this method. So much more robust and much more adapted to automation. Okay, so we've got this method to compute the transport. Yes?
The solutions at the end are these overall scattering times. You don't get a scattering time specifically for each kind of electron-phonon coupling. Is that right?
No, I mean, you can, if you want, separate it by thing, but no, in general, the solution, takes all phonons into account at the same time, and so the output of scattering time is not specific to a phonon, it's a global one. Because actually you can't, like in the equation, in principle you can't separate all the phonon modes. Yeah, I mean you can within certain approximations, but I don't remember how they're called. But yeah, to write that the 1 over tau is the sum of the 1 over tau's of each mode is an approximation. Mm-hmm. We don't use this approximation here. Yeah.
Okay, thank you.
So yes, we have this this method to compute the scattering times and thus the conductivity. Once you have the scattering time, the conductivity and mobility is pretty easy. And the first thing we did with it is to compute the mobility of several common 2D materials that are out there. So we have here phosphorine, hole side, and electron side, a bunch of TMDs, so MOS2, WS2, WSE2, and arsenine. And this is the mobility as a function of temperature. You can see it ranges almost to 2 orders of magnitude, and so we have a nice variety of performances here in terms of transport. And one interesting thing we noticed is that if you rank those materials in order of mobility, from high mobility to the left here to low mobility to the right, and then look at the Fermi surface, effectively like the Fermi level plus or minus temperature. This is the orange that we see depicted here, and all this of course the band structures. And you can see that the ranking corresponds to the number of valleys that are intersected by this Fermi surface. And so there's like a strong correlation between mobility and the number of valleys that in your system. That's because intervalley scattering, I said this I think already Monday, intervalley scattering is usually strong, and so when you have more valleys you have more intervalley scattering and the mobility goes down. Okay, so that was a very useful thing to notice. It actually pretty directly led us to the first application that I'm going to talk about. So it was with arsenine, so this material that we see here. And first we're going to look at a little bit more details on electron-proton coupling. So those plots are a bit complicated. I've been looking at them for years, and I tend to go a bit too fast in talking about it. So I'll take the time to explain what they are. So each subplot here is a phonon mode. And here we are looking at the electron-phonon coupling for each phonon mode. And we can see an initial state that is represented by a white star in each of those subplots. It's always at the same spot in this top valley here. And those 6 valleys are the 6 valleys in the band structure here. And every spot of color everywhere else is the electron-phonon coupling from the initial state to whatever final states elsewhere. Okay, and here we can see, I mean, the interesting thing that we see here is that the things that light up in red, so the strong electron-phonon coupling, are the valleys where the initial state is not. So this means that intervalley scattering or electron-phonon coupling is the strongest. So in particular, you can also compute the contribution from each phonon mode to the resistivity. And by the way, in this case, we did use this approximation of the scattering time to do this, so it's not exact, but here we're just looking at some idea, you know. You see that those 3 modes to the left here are the most important, and you can see that they are mostly intervalley scattering. So, okay, this is pretty clear that transport is dominated by intervalley scattering in this material. And what we noticed as well is that if you strain the material with a uniaxial strain, you're going to shift 4 out of 6 valleys up in energy. And once those valleys are above the Fermi level from a sufficient energy, they're effectively unreachable for the electrons. They don't participate in transport anymore because there's no electron energetic enough to bring them there. So if this energy is high enough, which it is for 2% strain, which is admittedly relatively large but not crazy, you get already like 160 millieVs of shift, which is huge and way more than enough to kill this intervalley scattering. And then you have a mobility that is improving by a factor 6 here. And so this works for arsenine, but this actually can work also for the whole family in which arsenine is, that are those group 5 buckled monolayers. You have antimonine and blue phosphorine, for example. And you can also think of this general principle of trying to break some symmetries and move the valleys up and down in general as a way to engineer mobility, and not necessarily with strain. You can think of other things, other ways to break the symmetries and break this degeneracy in the energy of the valleys. Okay, so as valley engineering. The next one is profiling high conductivity materials. So this is a very brute force materials design one, but this is a question that I've had during this week. Like, did I use machine learning at some point to find those materials? And the point is, I tried, and well, I'm not very good at machine learning, so I probably didn't try as well as someone else could have. But the point is, I usually ended up going back to looking at some physical arguments to find the materials and go and find some descriptors rather than like pure machine learning. So this is kind of what I'm going to describe right now, to try and just look at it and figure it out from a physics point of view. So here, to The idea is that we can't do this full transport workflow for all the materials in the database. It's quite expensive in terms of computer time. So we'd like to have an idea of whether a material is good or not for transport just by looking at the bands. And to do this, we learn from the best. So there are two materials that we know have a very high and very good conductivity, that we knew at that point, at least. And those are indium selenide and the whole side of phosphorine. And so if we look at those, there are kind of two different ways to optimize conductivity. Indium selenide has a steep and deep single valley. So steep means it's this valley we see here, the bottom one, is very sharp. So the velocity is pretty high, and obviously high velocity is good for mobility. But it's also deep in the sense that the next valleys that you encounter in the band structure are pretty high in energy. So this is around 0.7 electron volts, and so this means that you can dope this material with the highest you can dope with current experimental setups, which is like around 10 to the 14 centimeters electrons per centimeter square, and the Fermi level won't get anywhere near those other values, so you will stay in this single valley there. And this is essential because if it's steep, it's also relatively fast to fill up. The DOS is relatively low, and so it fills up fast. So it needs to be steep and deep. It just can't be steep. Then the phosphorine is a slightly different way to achieve this. There you have the valley is very anisotropic, so you have a high velocity direction and a low velocity direction, so low or high effective mass. Here, so of course you would want to do the transport in the high velocity direction, but the other direction also helps because it gives you some DOS, and in this case DOS is good because you get more electrons that go at this certain speed, and it also means the valley feels a little bit slower, and so you don't need it to be as deep as in the other case, because at standard kind of gate voltages, the Fermi level won't be that far in this valley. So an isotropic single valley is good as well. Okay, so then we go through our database and we filter all the materials. First we had 250 something materials with less than 6 atoms per unit cell. Among those there are 150 semiconductors, 110 with positive phonons, so dynamically stable material. And among those we look at those that are single valley, because both cases are single valley. You have 44 on the electron side, 13 on the hole side, and we also put a limit on the value of the gap because we're looking for a semiconductor, not a fully insulating material. And then from this, looking at the Fermi velocity, we figure out if it could be like steep and deep single valley like ANSE or an isotropic single valley like phosphorine. And we find 6 like INSE with the list that you have here, and 2 that are a little bit more like phosphorine with this anisotropic valley. And then we put those through the transport workflow. Now we have a dozen material. This is doable in a reasonable time. And indeed, we found that the conductivity and the mobility of all those materials is pretty high, like high compared to everything that's done these days in semiconductors. I'll put graphene out of this because it's a semi-metal and it's quite extraordinary. But in terms of semiconductors, those are all performing extremely well and also on par with 3D materials. The kind of caveat is that here we're looking at relatively highly doped material, and this is because we're using some really fermiology kind of arguments to find the high mobility materials, and so we need a Fermi surface. So we need to put the Fermi level inside the band structure, and so we need a certain density of carriers. But this actually helps us with the Fröhlich interaction that I also talked about during the week. So this is the interaction with the polar optical phonons. and that turns out to be screened at high doping. And so a lot of those materials, in particular the red ones that are electron on the electron side, are limited by Fordyce interaction and are doing well here because they're highly doped. We can see this in a little bit more details by picking one of them. So this is gallium selenide we see here. And if we compute its mobility either at high doping, so this is the point we just saw, or at neutral doping or small doping, here I'm going to take 10 to the 11 as being more or less neutrality, we can see a huge difference, like more than a factor 3, and the mobility goes down. And we can pretty much be sure that is for the Fordyce interaction by plotting here the mobility as a function of temperature, first in the neutral case, so this is the low situation. Then in orange, we just take out the polar optical phonons from the whole process. I mean, where in simulation we can do that. We just take it out and we can see already the mobility shoots up. So whatever happens, it comes from those phonons. And then compared to the doped case here, we can see that it's much closer. So whatever happens is corresponds to killing the coupling with the yellow phonons. And we saw already yesterday that this is exactly what free carrier screening does when you dope a material like gallium selenide. So you have here the coupling to the polar optical phonons as a function of momentum. Here in the neutral one, it shoots up at small momenta, but it dies if you dope your material because of free carrier screening. Okay, so this is partly what makes this material so good at high doping, but at low doping it's not so good. And we would like its performance to be somewhat a bit more consistent as a function of doping, because you do need also low doping for a lot of devices. And this is where the beauty of Van de Waals heterostructures comes in. We can think of ways to bring a property to a certain material by associating it with another material that has this property. Let me explain here what I mean. So transport happens always in this gallium selenide layer, but we said that we were missing this free carrier screening, especially at low doping. So we can try to bring this free carrier screening from some other material that would be next to it, and in this case it would be doped graphene. So that's the top layer here that I can call the screener, for example. And of course in between the two you need to add some kind of separator to isolate them electrically, otherwise you would just measure transport in graphene, and this is not the point. So the general idea here is that the polar optical phonons in gallium selenide are going to generate a Fordyce field, which is going to induce a free carrier density response in graphene, which itself is going to go back and screen the Fordyce interaction and help with this low doping mobility. We would like to check that from ab initio. And the challenge here is that those are very complicated things to simulate, those heterostructures. That's because we are, in DF10, we rely on periodic boundary conditions to essentially have calculations that are proportional to the number of atoms in the unit cell. And if we use a gallium selenide, we can simulate infinite layer of gallium selenide for a cost proportional to the number of atoms in the unit cell, that is just 4. But if we now put boron nitride, they don't have the same lattice, right? There's a lattice mismatch. And to find a common lattice that somehow matches both, this is called the commensurate lattice, or the Moiré pattern, if you want, you have to turn one with respect to the other and possibly strain a little bit each of the layer. And in this case, for example, even if you allow a relatively generous strain of 3% in one of the layer and turn all you want, you're going to end up with a minimum of 34 atoms per unit cell. Now, the cost of the DFT calculation grows as this n to the cube, and since we're talking about transport and phonons, there are also many other n factors that come in, and the calculations become way too expensive. And here I just put Bn, we would still need to put graphene on top. So it's very difficult to simulate all this directly in density functional theory. What we could do, however, is to use some kind of semi-analytical model. So here, this Fröhlich interaction and the screening from graphene and all this, in the end, it's just electrostatics. So it's not some very complicated interaction that's, you know, too obscure. So we can hope to simulate each of the layer ab initio to have some very material dependent, like realistic basis, but then simulate all those electrostatic interactions between them with a certain model. So this is what we did with this Van der Waals electrostatics model. So we start by extract the response of each single layer from density functional perturbation theory. So to do this, we assume a form for the response function that is the one you see here. It's the sum of monopole and dipole contributions with the corresponding projector functions f and g. And q and p here are just the amplitude of the response on each of those projection functions. Okay, the point here that I want to make quickly is that I plot f and g, those projector functions, and as you can see, they're not like simple like square function or triangle function. They're really material specific. They have those like non-obvious variations that really come from DFT simulation of the material. So those are specific, and then we built a database of those functions for every material that we need to put in our Van der Waals heterostructure. And then we just need, so from this we can reproduce the response of any single layer at essentially DFT accuracy. And then we need to put all those responses together to compute the combined response of all the layers in the Van der Waals heterostructure. And this is done in a kind of a mean field theory where we assume that each layer sees the other layers just as an external perturbation. So the perturbation potential for a given layer is given by the global external potential plus the sum of the potential induced by all the other layers. And from this you compute an induced density, an induced potential. And the trick here, of course, is that the induced potential of certain layers appears in the perturbation of all the other layers. So you have again a like a system of coupled equation that has the size more or less the number of layers in your Van der Waals heterostructure. To have a better idea, here's like an example with just two layers. So the layer 1 is perturbed by the external potential plus the induced potential from layer 2. And this is how you get the induced potential from layer 1 that's going to act here and so on and so forth. I think you can get the idea. So we solve this system numerically, and this gives us the response of the entire heterostructure, and this allows us to simulate the system. And yes, we can compute the response of the Van der Waals heterostructure to any perturbation. In particular, we can perturb it with the equivalent of the Fröhlich interaction. So the potential generated by a polar optical phonon. We know how it looks. We can extract this from DFT. So that's what we input in our system, and the output is what I show here effectively. So this is the this Fröhlich electron phonon interaction, and here just for reference is what we get in neutral gallium selenide, and this is what we get with still gallium selenide neutral, but with this doped graphene next to it. And as you can see, we get something very similar as what we got with this free carrier screening, except this time the free carrier screening comes from graphene and not the doping of gallium selenide itself. And then we can confirm that this indeed helps us with the mobility by computing the mobility at different doping level. So resolving all the electrostatics at different dopings. And thankfully we agree here on this point at high doping. But the most interesting here is that instead of losing all the mobility when we decrease the number of carriers at low doping, we keep a relatively high mobility because the free carrier screening from graphene kind of picks up the slack from the free carriers in gallium selenide. And yeah, so this is a very general way to enhance the mobility of not only Fröhlich limited materials, but effectively any material that is limited by a screenable kind of electron-phonon interaction can be improved by this general strategy. And so that's it. Yeah, I'll leave the conclusions there, and if you have some questions. Yeah.
Okay, go ahead, Cashel. Yes.
Well, let's see if I can phrase this properly. You know, when I first saw your slide saying there are 1,000, maybe 2,000 exfoliable systems that you would examine, and I was impressed. When I saw it today, my first thought is, why only those systems? There are lots of 2D systems that can't be exfoliated, you know, thin film growth or interfaces. Of course, those wouldn't have necessarily have van der Waals interactions with the neighboring layers. But I'm just curious how much of the physics you've been talking about this week might apply to more general two-dimensional systems, material systems.
So a lot of it is about not only the electrons but the phonons. So all the the quantum well stuff where the electronic system is 2D, but it's in a material that is 3D. Then the phonons are not necessarily 2D. They're so this does not really apply there. But on thin films, I mean, it depends, I guess, on the thickness. Maybe at some point you get closer to the 3D kind of physics. One interesting point I would have for this is that, so in this application here, you need the graphene to be relatively close to the gallium selenide to screen this, because this, of course, gets weaker and weaker as a function of distance. And this is something you can do nicely with 2D materials and this really optimized layer atomic thickness. So we can just get by with just 1 BN. I mean, 1 BN is the ideal case, but 2 or 3 BN would be good too. But yeah, if you put there something that starts to be 10, 15 layers, you probably lose the effect mostly. So yeah, some of it would be applicable, but maybe not all.
Okay, so for our next question, I'm going to call on Jesse. I'm just going to turn on the volume for as long as I think you're asking your question.
Thanks. So yeah, very interesting. So I was wondering, when you're talking about designing, tailoring mobility or other properties via van der Waals superstructures. And so, you were saying that you can modify the electron-phonon coupling, but it seems like you also, are going to you're reducing strain by layering these materials, which you said earlier. The talk also changes the mobility by changing the different values. And so I don't know if there are more effects too that might occur when you layer these materials. And do you think that your theory can sort of get it all? So you can really predict these are the materials you layer, and combinatorially figure out out of all the possibilities, this is going to be a good one, or is it going to be you're going to have to do the experiment and figure out which are the effects that really come into play when you layer these materials?
Yeah. So can we find all of them? I don't know. Those, there is not really a systematic kind of way to look for these things. It's just come up, and it's just ideas that come up as. It would be nice to kind of do this more systematically. I think, of course, this is design at a very still at a very theoretical level, even if it might look to theoretician quite applied, it's still very theoretical. So of course there's a bunch of problems, obstacles that are going to come when it comes to making this in experiments. So I don't know. I would say this screener thing is relatively easy to do experimentally. I mean, people do those kind of heterostructures already. Maybe the contacting would be a bit complex here. Not sure, but straining is a bit more difficult. Yeah, this is up to like really collaboration by collaboration with experimental people, and we see how things are doable. I'm just trying to find some ideas there.
Yeah, thanks for the nice clothing talk. So I have a question on this remote screening. So does this Coulomb drag effect is automatically captured in the calculation?
No, not at all.
Okay.
No.
And the other question is, I noticed on the first slides, you showed one of the material is bismuth telluride, which is now known as topological insulator.
Yeah.
Now, it has a conduction surface, which is topological surface state. But have you implemented the calculation of like this surface conduction?
No. Well, in addition here, there's no sock. Yeah, maybe I should have mentioned this. At least put this in the thing. There's no spin-orbit coupling in those particular transport calculations. I can do it. The includes spin-orbit coupling. That's not a limit. Now the surface or edge state or this kind of transport. Well, in DFT there's no edges, so it's kind of a bit more complicated. Although I guess like all you need are no, you would need the scattering of the edge states, which is different from the bulk states. Here I have the coupling elements for the bulk states. And this is interesting. This is something I've thought about doing, but difficult.
Yeah, because it is deemed that it is the bulk, surface state that the carriers in the surface state that are highly mobile.
Yes.
In this type of materials, topological insulators, right?
Yeah. So I guess for this material it would be if you're in the gap, you would have some edge states going, and then if you're above the gap in the conduction band, which is this case here, you have some bulk states conducting, and it's conducting all the time, and so you lose a little bit this on-off idea. That's true.
Thanks.
Okay, my question is actually about the same thing. And now you confused me because these are already monolayers, right? So are the crystal structures different than for the bulk bismuth selenite, or is it basically like just one of these 5-layer blocks or whatever you have in bismuth selenite?
So he was talking about the bulk material.
Two-dimensional bulk.
But I don't know if it's bismuth selenite. I think some of those might also be like topological, have some conducting edge state in 2D.
Oh, I see.
I'm not sure which one.
But in a sense, they're already all surface.
Yeah. It's different.
So my other question was, well, if you know indium selenite is good, and that was your starting point, it wouldn't be hard to guess gallium selenite, right? But these other ones, are they all related to the bismuth selenite there? And can you gain some insight after the fact that you found these ones now in how their crystal structure affects ultimately their mobility?
Absolutely. So this is a question that comes back now and then. I'm not very good at chemistry and like the structure and the bonds and why this comes. Those formulas come there. I usually just look at the band structure. So I'm really start from those band structure. But indeed, like so you have those Bi or SbX3 with X being the telluride or selenide. I think the BiClte and aluminum LiT2 are a bit different, and so this could be like new families to explore. And those two, the two whole ones also are quite new. But there's certainly some chemistry thing to arguments to be made. I haven't really done them.
Like you have gallium selenite seems better than indium selenite, so you might guess, well, what about aluminum selenite?
So I don't know
The
if
next
it's
one in the periodic table.
if it's exfoliable. So if it's in the database, it should have gone through the same filtering, and if it doesn't come up, it just maybe it is also pretty good with high velocity, so low effective mass and all this, but its valleys, like the next valleys in the band structure, are a bit lower for some reason, and then all the deep and steep single valley idea just breaks. So yeah, the chemistry don't get you all the way. I think you need to look at the band structure at some point.
Well, I guess in light of the time, I think I'm going to end the formal proceedings here. Thibault will be here in the afternoon, of course, for more discussions. But I guess this is the last of the lectures in our series. So thank you very much. This has really been a magnificent series of talks.
Yes, thank you. Thank you so much for this week.